So if we know this film temperature, we can now know the properties of our fluid, our air, and we will be needing some informations from readily available informations based from the properties of the air. So we need to consult some table for the properties of your fluid. So I have here the table for the properties of air. Okay. Again, I've searched for the properties of air at certain condition. Then if your given fluid is not air, then you must search for another property table. Okay. But since our problem is regarding air, so I have presented to you the properties of air. Okay. So as you can see here on the left, we have the data for the temperature, and this temperature is what we call the film temperature. Okay. So based from our computation, the film temperature as the average of the surface temperature and the fluid temperature is we have 45 degrees Celsius. So we need to locate the 45 degrees Celsius here. So we need here. Okay, and from here you need to project to the right side of this table to know the different properties of air. Okay, so from here you can now know the value of your density, the value of your specific heat K, the CP pala to, CP, the thermal conductivity, right, the thermal diffusivity, the viscosity, the kinematic viscosity, the dynamic and the kinematic viscosity, as well as the Prandtl number. Okay, so if we project it, we can now have these values. Okay, it's easy, right? Okay, going back, let me write it here. If our film temperature is 45 and our fluid is air, so we have the following data. Okay, so we can use these values to solve for the value of our RE, wherein our Reynolds number is equal to the density, the stream velocity, the characteristic length, all over the dynamic viscosity. Okay, so from here the density is equal to 1.109. So let me copy. Okay. So our density is 1.109. Our stream velocity is already given. Where is our stream velocity? Here. Our stream velocity is 0.5 meter per second. So we have 0.5 meter per second, and our characteristic length is also given. We have a 2.5 meter, right? The length of our panel. Then it is all over to dynamic viscosity, which is this one, 1.9 41 times 10 to the negative 5 kilogram meter per second. Okay, so can have kilogram, 1, 2, 3, 3 seconds. Okay, so we have a dimensionless number RE, and this is equal to, if you're gonna calculate this, we have a Reynolds number equal to 71,419. Okay, so this is dimensionless. And then to know the flow, going back, diba, need to determine the flow using our Reynolds number. Okay, so our RE is 7419, and if you can also still remember the RE, if we have a flat surface, so that we have the critical is equal to 5 times 10 to the 5. Okay, or it is also equal to 500,000 Reynolds number. Okay, 1, 2, 3, 4, 5. Yeah, it's equal to 500,000. And if we're gonna compare these two, our RE to our RE critical, it is below or above 500. Okay, it is below. So since it is below, therefore our RE, or the flow of our air, is laminar. Right, so we have a laminar flow. If we know that this is laminar flow, then we can now proceed to the correlation of these two. Okay, since we will be calculating this condition, so let us assume and use the average value of the condition to represent this one. Okay, so let's use the average. Okay, under the laminar, we use the average and nu bar. Then we can now have our Nu is equal to 0.664 Re 1/2 PR 1/3. So we have Nu is equal to 0.664 Re 1/2 PR 1/3, right? So we can now compute the value of our Nu, 0.664. Our Re is 71419 raised to 1/2, and our PR is, where is our PR? This one, 0.7241, 0.7241 1/3. Okay, but let us go back muna again here. Since our condition is that we need we can apply this correlation if we have a PR value greater than or equal to 0.6, and since our PR is 0.7 something, then it is greater than 0.6, so we can use this. Okay, so we can use these conditions or correlations. Okay, so yeah, so from here we can now compute the value of our Nu, which is equal, I think it is equal to 159.3 average. Okay, so if we already determine the value of our Nu, going back to our equation 1, that our Nu, I mean this one pala, equation 2, our Nu is equal to HLC over K. HLC over K, wherein our H is unknown, our LC is 2.5 meter, our K, where is the value of our K? our K is 0.2699. Point 0.2699. So we have 0.02699, and then the value of our NU is 159.3. Then we can compute for the value of our H. And if you do a simple algebra here, you can now compute this one H. Then our H is equal to 1.72. Okay, so that is the value of our H. And then let me complete first. So we have what they call this, the K is equal to watts per meter K, right? So we have a the unit of our H is equal to watts per m squared K, right? So that is our K. And then if we already know this 1.72, then we can now go back in our this one, in our equation 1, wherein our H is equal to 1.72 watts per meter square K, or temperature. Okay, so from equation 1 we can now know the value of our Q is equal to 1.72 times 2.5 by 2.5 by 50 degrees Celsius. Okay, so we can cancel this out. M squared. So we have the value of our Q is equal to watts. So we have a 537.4 watts. So this is our Q loss, rate of Q loss from a solar collector. So once again, let us review. We have this problem, need to find the heat loss, and we illustrate our condition, and we know that we have a flat surface condition, and we follow some formulas and conditions for a flat surface. Then we say that our heat loss is given by this equation, but we don't know the H. So to find the value of our H, we use the Nusselt number and the correlation. But in order for us to determine those numbers, we need the surface film temperature and use it in this table so that we can know the properties. And having those properties, we can now go back and compute our Reynolds number. And after having our Reynolds number, we can now tell if our flow is laminar or not. Okay, and then after that, if we already know our flow regime, then we can now use this correlation. Having this correlation, we can now have the value of our NU and use this formula to find H. Then after finding H, we proceed and go back to our equation 1 to finally find our heat loss. Okay, so that's all, and see you on our next video for another example.